All right, here we are at the final section of Chapter 6 on quadrilaterals. Today we're talking about our last couple of quadrilaterals, the trapezoid and the kite. So we'll look at properties of each of those and then use those properties to solve for missing parts in each of those quadrilaterals. I'm going to try and keep it shorter for you guys today, but if at any time it's too fast, you need to go back over the video to hear certain things, or you need to pause it to get things down, that's fine. But just make it your own pace today. All right, definition and properties of a trapezoid. Anything in bold, you're going to want to make sure you add into your family tree. So from the definition of a trapezoid, we know it's a quadrilateral with exactly one pair of parallel sides. That's the first property of trapezoids that we want to acknowledge. Exactly one pair of parallel sides. And because it's only one pair, a trapezoid is not a parallelogram. It's in a different grouping, separate from the parallelogram family. So as you look at the facts and characteristics in this example here, you can kind of see the different parts that make up a trapezoid. The bases are the parallel sides. The legs are the other two sides that aren't parallel. And then, of course, the base angles. There's going to be two pairs of each of those in any quadrilateral. So here's a pair of base angles, D and C. Another pair of base angles is A and B. Okay, so those are the base angles. And then we'll talk about a special kind of trapezoid, the isosceles trapezoid. But first, let's finish getting properties of any trapezoid. Okay, so here's our family tree so far. We got one pair of parallel sides from the definition. Okay, that's from our definition. That's in your family tree. Because we're dealing with parallel sides and parallel lines, we know that same side interior angles are going to be supplementary. That comes from what we learned in Chapter 3. But same side interior angles, meaning angles along the same side, those are supplementary angles. And they have to be in between the two parallel lines to be same side interior. So those are adding up to 180 always. Okay, isosceles trapezoids are a special kind of trapezoid. Again, here anything you see in bold is what you would add to your family tree under isosceles trapezoids. But each of these properties will also kind of help you identify the difference between a regular trapezoid and an isosceles trapezoid. So the first big thing for isosceles trapezoid is it's got each pair of base angles congruent. Okay, if you know it's isosceles, then you know each pair of the base angles are going to be equal angles, and that's shown in that top picture there. Another property, if a trapezoid has one pair of congruent base angles, then it is an isosceles trapezoid. And again, that kind of follows from this first property, so we don't really need to add that into our family tree. And the last special thing about isosceles trapezoids, the diagonals are congruent. So when you draw in those diagonals across the trapezoid, those are both the same length or congruent. So here's what our family tree should look like now. With the isosceles trapezoid, we know the legs are congruent. That came from our definition of regular trapezoids. And then base angles are congruent and the diagonals are congruent. Those are all the key properties of isosceles trapezoids. So if you know you have an isosceles trapezoid, you can use those to find missing parts. So let's go ahead and do that. We want to use properties of isosceles trapezoids to find missing information. Here we've got a speaker from a sound system shaped as an isosceles trapezoid, and we're given some info up here about different pieces of the speaker. And we're going to find some different measures. So first we are asked to find what's the measure of angle FGH. That's this whole corner of the speaker. Okay, so we're finding a missing angle, so let's look at our given information and see what other info about angles we know. And right here we've got the measure of angle FJH, this corner down here, is 85 degrees. All right, so we want to use that angle to find the angle opposite it in the trapezoid. Since this is an isosceles trapezoid, what do we know about the angles? Well, the base angles are congruent. So angle J and angle H, that's a pair of base angles. They're congruent. The other pair of base angles is angle F and angle G, or angle JFG and angle FGH, which is the one we're trying to find. All right, so we know base angles are congruent. We also know that same side interior angles, so angles along the same leg or the same side, are supplementary. They have to add up to 180. So those two properties right there of isosceles trapezoids are going to help us find our missing angle. Base angles are congruent, so we know angle H here is 85 degrees. And then angle FGH and angle H have to add up to 180. So all we need to do is take 180 minus 85, and we'll get our missing angle. (95 degrees for angle FGH, using properties of isosceles trapezoids and trapezoids. All right, another example with the same speaker. Now we want to find the length of KH, which is part of the diagonal. So we need to look at our given information and see, okay, what do I know about the diagonals so far? We're told FK is 8 inches, so this part right here is 8 inches. And JG, which is the whole other diagonal, JG, altogether is 39 inches. And we want to find the other part of the other diagonal, KH. All right, diagonals in a trapezoid. If it's an isosceles trapezoid, we know that the diagonals are congruent, so FH is also equal to 39 inches, which means FK plus KH has to add up to 39 inches. Those are the two parts of this diagonal. So those two parts together have to equal the whole length, 39. We know FK is 8. We're missing KH, but we know the total is 39. All we do is subtract 8 from 39, and we find the length of KH is 39 minus 8, or 31 inches. To satisfy properties of isosceles trapezoids, that's got to be the length of KH. All right, again, we've been doing a lot of coordinate proofs with quadrilaterals, and we can do the same for trapezoids. If you've got the 4 vertices like we have here for quadrilateral ABCD, you can show that it's a trapezoid and then determine whether it's an isosceles trapezoid, so getting a little more specific. So for the first part, showing if it is a trapezoid, we need to look for, is there one pair of parallel sides? Remember, that's the definition of a trapezoid. So for parallel lines on a graph, we need to look at the slope and see, do opposite sides have the same slope? And we only need one pair. But if both pairs are parallel, then it's not a trapezoid. That's going to be a parallelogram. You just want one pair of parallel sides. So we use our slope formula, which we've reviewed a lot in this chapter. Rise over run, or y2 minus y1 over x2 minus x1. And ultimately, you have to do that for each side. So AB, that'd be 1, x1, y1, x2, y2. Then do it over again for CD, where C is your x1, y1, D is your x2, y2, so on and so forth. Check to see, do you have one pair of parallel sides? And if that works out, yes, it's a trapezoid. Then we go over here to see, is it an isosceles trapezoid? In isosceles trapezoids, we need to look at the legs. Does it have congruent legs? Because that's the definition or key factor of isosceles trapezoids. So if we're talking about congruency, we want to use the distance formula, because that gives us length on a graph. And again, like we've reviewed a lot of this chapter, that's our big square root where you subtract the x's and square them. And then do the same thing with the y's, y2 minus y1 squared. And in this case, we're not doing it for all four sides, we're just doing it for the legs, the non-parallel sides. And in this case, that would be A, B, and D, C. You can see it when you graph it. You can also get it from our check for if it's a trapezoid or not, which are the non-parallel sides. Those are the legs. So that's how we would do a coordinate proof for trapezoids on the graph. You'll get some more practice with these kind of problems in class. Okay, one other thing about trapezoids in general, any trapezoid, is this trapezoid mid-segment theorem. And I want you to add this to your family tree. Again, just kind of the stuff in bold. The mid-segment, we need to get that to know you're talking about the mid-segment. The mid-segment of a trapezoid is parallel to each base, so that's shown here in this first diagram. But here's the big thing that we'll use the mid-segment with. The mid-segment is 1/2 the sum of the lengths of the bases. So let's say you know each of the bases. We'll say this first base is 3 units, and the bottom one is 6. All right, to find the length of the mid-segment, we just add the two bases together, 3 plus 6, and take 1/2 of that, or divide it by 2. So the length of the mid-segment would be 9/2, or 4.5 units. Okay, that's the basic practical use of the mid-segment theorem. Also, maybe note this in your family tree or off to the side if you're running out of room. The mid-segment is also referred to in your books as the median of the trapezoid. I'm not sure why, but those are used interchangeably. So know that the median is the same thing as the mid-segment and has this same property or theorem. All right, so here's our family tree. You added the mid-segment theorem here at the bottom. And again, you can just shorthand it like that. That's the key thing we want. That's for any trapezoid. So isosceles trapezoids or not, the mid-segment theorem applies. So let's use the mid-segment theorem to find a missing length. All right, we're given the length of the mid-segment here, and one of the bases, we want to find the value of x, which is the missing base. So by the mid-segment theorem, we know that the sum of the bases, we add them together and divide by 2. That whole thing is equal to the length of the mid-segment. So I just plugged in what we were given for this particular trapezoid. And now we'll solve for x. So right now we have a big fraction over on the left. I want to get rid of that 2 in the denominator, so we just multiply both sides by 2. Let me change colors so we can kind of see that better. If we multiply both sides by 2, over here the 2's cancel out, and then we just simplify everywhere else. So we got 18.2 plus x equals 15 times 2, or 30. And now subtract 18.2 from both sides to finish solving for x. And x, our missing base, is going to be 11.8. We weren't given any units, so we can just leave it at that. 11.8 is the length of the missing base of the trapezoid. And that's using the mid-segment theorem. That's the other application besides the one I showed you in the last slide with the example of the mid-segment theorem. All right, so let's move on to kites, the last of the quadrilaterals we're talking about. 2 things to take from this definition, and then we'll add 2 more properties after that. So leave yourself some room in your family tree. But go ahead, add the property from its definition. A kite is a quadrilateral with exactly 2 pairs of consecutive congruent sides. And again, remember the consecutive part means sides next to each other. So you can see it in the example here. These 2 sides next to each other are congruent. and these two sides next to each other are congruent. Those are consecutive sides to show it's a kite. Another thing to note in your family tree is that opposite sides of a kite are not congruent and they are not parallel. So when we look across kites, you'll see opposite sides aren't congruent and they're not parallel to each other. So again, a kite is not a parallelogram. It's in a separate part of the quadrilateral family tree from parallelograms because it's not meeting those conditions. All right, two other properties of kites to take note of and add to your family tree. The first is that the diagonals are perpendicular. So the diagonals bisect each other. When they intersect each other, they are meeting at a right angle. And if you want to note in a diagram, one of the diagonals is always going to be bisected, and it's the shorter of the diagonals here. That's going to be bisected by the other diagonal, but the longer diagonal is not bisected. Okay, but the key thing is the diagonals are perpendicular, and you can use the perpendicular symbol for the shorthand. Remember the upside down T. The other thing with kites is that there's exactly one pair of opposite angles that are congruent. Only one, not every pair, but only one pair. And you'll see that marked here, angle J and angle L. And again, those are the two angles connected by the shorter diagonal, the one that's cut in half by the longer diagonal. All right, so add those to your family tree. And here we are, finished with the quadrilaterals family tree. Make sure you've got all those properties of kites, and you can double check your trapezoid as well. All right, let's look at a couple quick examples of using the properties of kites. It's really easy, really straightforward. First, we're going to practice finding angles. All right, we want to find the measure of angle GFJ, which is this one right here. And we remember with angles and kites, there's one pair of opposite angles that are congruent. Of the pair we're given so far, 128 and 72, those are not congruent, so it must be angle GFJ and angle GHJ that are the congruent angles. So let's say those are each x, and we're trying to figure out what is x. All right, this is a quadrilateral, so all of the angles, all four angles should add up to 360 degrees inside a quadrilateral. And now we just add up our angles. We have the two missing angles, 2x plus 128 plus 72. So let's combine our like terms. 360 equals 2x plus 128 and 72, 200 even. So now we subtract 200 from both sides, and we have 2x equals 160. And all that's left is to divide by 2. 160 divided by 2 is 80. So our missing angle, angle GFJ, is 80 degrees. One other use of properties of kites, remember the diagonals are perpendicular, and when we mark that, we notice again inside of our quadrilateral we are creating a triangle, those shapes that we know so well from the last few chapters. So we can find missing sides of a kite using right triangles. In this case, we want to find ZY. So we've got 8 and 24, which sadly are not part of one of our Pythagorean triples. Remember, keep those memorized, always in the front of your mind, so you can have shortcuts in problems like these. But in this case, 8 and 24 are not part of a Pythagorean triple, so we've got to just plug into Pythagorean theorem. 8 squared plus 24 squared is going to equal ZY, our missing side, squared. So 64 plus 576 equals ZY squared. Let's add up our like terms. 64 plus 576 gives us 640. And we take the square root of both sides to get our final answer. Square root of 640 is to the nearest, let's go nearest tenth. It's going to be about 25.3 units equals the length of zy. All right, so we used properties of kites, the diagonals are perpendicular, and properties of triangles to find a missing part of that quadrilateral. All right, that is it for trapezoids and kites. That is it for quadrilaterals. Again, if you need to go back over any parts of the video, go for it. Pause it, take notes that you missed, get those examples worked out in your notes, and we will practice these next time we're together.